22nd T. Ramchandran lecture series. We're sorry for the delay due to some technical issues. We thank all the respected dignitaries present here for joining us. We welcome Professor T. Ramchandran, who is responsible for today's PR lecture series, the Director in Charge, Professor Umesh, our Chief Guest, Professor T.S. Prasanna Kumar, who is joining us here from IIT Chennai to deliver today's lecture, Professor K. Narayan Prabhu, the Head of the Department, Metallurgical and Materials Engineering, all faculty members and students. Thank you for being here. We will start today's program with an invocation by Shruti PM.
Tukar.
We request Professor Umesh to accept the bouquet as a token of our appreciation. And Professor T. Prasanna Kumar for joining us today. I now request Professor K.N. Prabhu to address the gallery.
Distinguished Chief Guest of today's function, Professor T.S. Prasanna Kumar, Founder, Head of our Department and Guest of Honor, Professor T. Ramchandran, President of today's function and Director in Charge of NITK, Professor G. Umesh, my esteemed colleagues, distinguished guests, invitees and my dear students. A very good afternoon to all of you. It is my proud privilege to welcome you all to this 22nd lecture under Professor T. Ramchandran lecture series. We are all very happy to have with us Professor T.S. Prasanna Kumar, Professor, Department of Metallurgical and Materials Engineering, IIT Madras, who has readily agreed to deliver the lecture this year. At the outset, I'd like to brief you about the genesis of this lecture series, particularly for the benefit of student audience and young faculty. This is the 21st lecture and 22nd lecture under Professor T.R. lecture series, which was started in 1991. Professor T. Ramchandran was the founder head of our department. He joined our department as professor and head in the year 1965 and was mainly responsible for building up of the department and for developing infrastructure and sound base for research. Above all, he has been a good friend and guide to his students and colleagues. During his tenure here, he also served as principal of ARSC, now NITK, for 2 years. In 1973, Professor T. Ramchandran was honored by the Metallurgical Engineering Department of Banaras Hindu University, Varanasi, the Distinguished Alumnus Award. During 1975 and 76, 1983, 84, and 1990, after 1990, he was visiting scientist at the Max Planck Institute for Ferrous Research at Düsseldorf, Germany, from where he obtained his doctoral engineer degree. He retired in 1989 after 24 years of fruitful service to this institute. Thank you very much, sir, for coming here and gracing. The idea of starting this lecture was originated from the ex-colleagues of Professor T. Ramchandran and students at the time of his retirement. They generously contributed and established a fund to which the funds generated from the national seminar Madras 89 that was organized by the department to coincide with the superannuation of Professor Ramchandran was also added. The interest earned from this fund is being utilized in arranging a lecture every year by an eminent metallurgist in honor of Professor T. Ramchandran for the benefit of students and staff. Recently, some of ex-students and colleagues as well as children of Professor T. Ramchandran, Dr. Ajay, Dr. Ashok and Anita have contributed towards this fund. We are particularly thankful to Dr. V. Ramchandran and late Dr. Raghunath of United States of America who helped us in mobilizing funds for this lecture series by contacting the old students of our department settled at USA. Mr. V. Ramchandran, though he was here for a very short period, is still in contact with us and still helps us in mobilizing the funds. Special thanks to Dr. Prakash Babu, our alumnus of 1972 batch and one of the contributors to TR lecture series. He has donated a sum of $10,000 this year, and this has helped us to enhance the corpus fund to 10 lakhs. The fund is now transferred to the institute and would sustain the lecture series in the coming years. We at the Department of Metallurgical and Materials Engineering thank his honest and selfless effort in making this lecture series financially self-sustaining, and this will also take care of the inflation and gives us the flexibility to invite reputed and distinguished persons in the field of metallurgical and materials engineering from any part of the world. The names of the contributors to Professor TR lecture series are printed in the lecture booklet, which will be distributed later. We are extremely happy to have with us today former faculty of NITK and a close associate of Professor T. Ramchandran, who also happens to be my guru, Professor T.S. Prasanna Kumar, to deliver this year's lecture. He will be delivering a lecture on metallurgical process modeling for plant applications. I take this opportunity to introduce our chief guest, Professor T.S. Prasanna Kumar. Professor T.S. Prasanna Kumar graduated securing 8th rank from the University of Mysore with B in Mechanical Engineering, that is in the year 1969. He completed his postgraduate studies in Indian Institute of Science, Bangalore in the year 1979 and obtained ME in Foundry Science and Engineering, securing first class. He obtained his PhD from the Indian Institute of Technology, Madras in the year 1986. He was employed at the Mysore Electrical Industries Private Limited, Bangalore, that's from 1969 to 1970, and National Institute of Engineering, Mysore, from 1972 to 1974, KREC, Surathkal, from 1975 to 1990, and at Tata Steel, Jamshedpur, from 1990 to 1999. Currently, he is serving as professor at IIT Madras in the Department of Metallurgical and Materials Engineering. In the year 1981, he founded the Mangalore chapter of Institute of Indian Councilmen, and he was also responsible for starting a postgraduate course in advanced manufacturing engineering at KREC, now NITK Surathkal. Moreover, he has set up the CAD-CAM laboratory at KREC Surathkal. At Tata Steel Jamshedpur, he installed high-end finite element analysis facility and was responsible for setting up of the process modeling and CAD/CAM group and developed a number of mathematical models for metallurgical applications. He has developed software for SAFE, RDCS, then Hospesty, ISRO, VSSC, and National Fusion Project. Professor T.S. Prasanna Kumar has designed and developed a quench probe for quench heat treatment and incubated Thermal Solutions Private Limited at IIT Madras. Professor T.S. Prasanna Kumar specializes in process modeling, inverse heat conductance, finite element analysis, metal casting, heat treatment, and software development. He has published 75 papers in various national and international journals. He has also published about 20 R&D reports. On behalf of the Metallurgical Engineering Association and also Department of Metallurgical and Materials Engineering, I extend a very warm welcome to sir. I extend a hearty welcome to Professor T. Ramchandran, our guest of honor. Sir, we are honored by your presence. Professor G. Umesh, D. RNC, and Director in charge has kindly agreed to preside over the function. He is a constant source of inspiration in all activities of our department. On behalf of me and Department of Metallurgical and Materials Engineering, and on my personal behalf, I welcome you. I once again welcome all of you to this 22nd lecture in Professor T.R. lecture series. Thank you very much.
Thank you, Professor Prabhu. We now request Professor T. Ramachandran to kindly share a few words with us.
Professor Umesh, Professor Prasanna Kumar, Professor Prabhu, fellow members of, I should say, members of the Metallurgical Engineering Association, and you see how the memory goes back. And ladies and gentlemen, I say this every year that I'm delighted to come here, and I always say it's a pilgrimage every year that I make. And it's always a pleasure to come back to Surathkal, KREC, or NITK, where I spent very fruitful 24 years and happy 24 years. The campus was fine, the college was fine, everything was fine. The last 3 years, we had 3 people belonging to the graduates of this department giving the lecture. This year we have Dr. Prasanna Kumar, who though not an alumnus of our department, belonged to the department for quite some time. He did a lot of his work done in NITK, in our department, and was an inspiration to people like Prabhu and others. In those years, of course, we had an open house. I hope it continues today. We had even one person from Bantwal doing his complete PhD work in our department. And in that vein, also Prasanna Kumar did a lot of work in our department. And my association with him was that he was soon after he graduated, he joined KRC for a short while, 2 years or so. And at that time itself, because of our common interest in foundry, we used to meet and discuss. Later, he left and joined a private firm, came back, and it was then that our association became even greater. The enthusiasm with which he worked on initially on heat transfer modeling and later in other fields is an inspiration for everybody. And his greatest contribution to the department, I say, is Prabhu, because at one stage it seems he was interested in getting me over to IIT Madras. So Because he didn't so he got promoted here. So that's also a contribution to this department. I almost every year I have been talking about the department and how many people contributed to the progress of the department. But last year I made a departure and made a single point appeal. And I think I will do this year also, because it's something which is close to my heart. We have started a large number of IITs, NITs, and other institutions without knowing where the staff would come from, so that there is a shortage of staff in all the places. In fact, this mentoring of IITs by other IITs made it even thinner, because the same people have to work in two different IITs or NITs. So last year I made an appeal, and because I think it's a very fulfilling career. You may get more money in some other, especially the IT industry, but the satisfaction which you get by reading, getting knowledge and imparting knowledge and creating knowledge, that is something which you will only get from a teaching and teaching or teaching and research institution. We are very much in shortage of teachers, and it is essential that many of you must take to teaching. I have seen this as a personal experience. In India, the importance attached to teaching and research is not all that great. Not many people take an active interest in this. This is in contrast to the other Western, whether it's Europe or America. A very large considerable percentage of very bright people want to go for teaching, even though they may get better paying jobs outside. And that's essential if the nation is to be run. And therefore, I will, without extending it too much, I would say, I would request at least some of you to take up teaching as a career. All that is left for me now is to thank the Metallurgical Engineering Association, the Department of Metallurgical Engineering, and all of you for inviting me here again. As I said, it's an opportunity for me. In fact, this is the only opportunity where I get to talk metallurgy. Otherwise, I can only read in some. But here, I can talk to people on metallurgy. And to all those facing crucial examinations, my best wishes. Thank you.
Thank you, sir, for your kind words. The annual transactions of the Metallurgical Engineering Association and the Metallurgical and Materials Department (MITK) are published every year under the name Midcast, which is our department magazine. This year, we are proud to present the e-version of the magazine for the first time ever as an effort to go green. I request Professor T. Ramchandran to launch the green version of Midcast.
As you can, I'll come there. Yes, you can my personal email. You can this way. This is what it is.
Prasanna Kumar, Professor Prabhu, our esteemed professors from the Department of Metallurgical Engineering, my colleagues, and dear students. It is always a great pleasure to participate in this Ramchandran lecture series because it brings Professor Ramchandran to our campus. His presence here is always a source of encouragement and inspiration for all of us. So we are indeed very happy to have you here back in our campus once again, and I consider it as my privilege to be welcoming you to our campus in whatever capacity that I hold now. I'd like to express the same feelings on behalf of our director, Professor Surathkal. We are indeed very grateful to both Professor Ramchandran and Professor Prasanna Kumar to have found time to come here, talk to us, interact with us. Ramchandran lecture series, since I joined this institute in '92, is something which I always look forward to because it gives us an opportunity to listen to new work, to people who have been working actively in the frontiers of materials technology, materials engineering. I always fondly recall some of the past lectures which I heard under this program. If we really look at different activities of our institute, this is one of the flagship programs which happen every year. Consistently every year we have this lecture series, and I must congratulate both the Metallurgical Engineering Department as well as the Metallurgical Engineering Society for persisting and finding ways to sustain this lecture. It is heartening to note that the funds have really become sufficient now, that out of the interest from the funds, we will be able to support this lecture series in future. That simply points out the reverence with which Professor Ramchandran students hold him, the reverence with which his colleagues hold him, and we hope that this spirit will continue. We hope that such a effort will happen with other departments as well, so that in the near future we'll have a couple of more lectures of the same type in the institute. The topic for today's lecture is metallurgical process modeling for plant applications, and by all accounts I think we have one of the finest persons who could talk about this. It is very nice to know that he had been associated with our institute in the past. Sir, to just point out to you, we have a MOU now with IIT Madras, and under that we have more avenues for interaction with different departments of IIT Madras. A couple of months back we did visit your department, and we did talk to a couple of your colleagues to enhance our scope for interaction. We would like to, under the MOU, we have opportunity to send up to 10 students every year during the summer for summer internship. We look forward to very close interaction with your department. I am also very happy to see the large gathering here, the young students. You would, once the lecture is over, you will yourself realize that this 1 hour which you will spend will perhaps be something which you will remember for a long time. I would like to once again thank Department of Metallurgical Engineering for giving me this opportunity, and conclude by saying that it's always a delight to participate in this particular program. Thank you very much.
Thank you, Professor Umesh. As a token of our appreciation, we would like to present a memento to our chief guest, Professor T.S. Prasanna Kumar. May I request Professor Umesh to please present the memento. Professor K.M. Prabhu to kindly present a memento to Professor T. Ramchandran as a token of our appreciation. We call upon Professor K.R. Udupa to kindly present a memento to Professor G. Umesh. Thank you, sir, for being with us today. I thank all the dignitaries for being with us today. We will now move on to the lecture. I call upon Professor T.S. Prasanna Kumar, who will now be speaking to us about metallurgical process modeling for plant applications. Thank you.
Very good afternoon to you all. Thank you very much. Sir, Professor Ramchandran, this has been a great day for me. Thanks to Professor Prabhu, Department of Metallurgical and Materials Engineering, NIT, Surathkal, the association behind it. I deem it a great privilege and honor to present this lecture in the honor of Professor Ramchandran on this day, 2nd November 2012, under the auspices of the Department of Metallurgical Engineering. Before I start off with this presentation, I would like to reminisce about my association with this institute. I don't think this honor has been bestowed to any employee, ex-employee of any institute. This is, maybe I can easily recall at least half a dozen occasions where I was called and honored in some fashion or the other, even though I had left this institute some time back, in pursuit of something which the adage says, the grass is greener on the other side. Only when you go to the other adjacent pasture, you will see that after all, story is the same everywhere. And in this connection, I congratulate Professor Prabhu for having stayed here, maybe resisted the temptations of going elsewhere, though I know he had many occasions to seek what I tried, but did not maybe succeed. You have a wonderful department headed by a very good researcher in Professor Prabhu, and I'm sure all the students of this department are lucky to get that kind of support from the department and the institute and all the colleagues or the faculty of this department. I wish you all well, first of all. That was the time when I was associated with this institute between 77 and 86. Professor Ramchandran was such a support during my initial years. Though I was in the faculty of mechanical engineering, as you rightly pointed out, I did all my work in the Department of Metallurgical Engineering under his guidance. He was a singular person supporting me in my academics. I was drawn to him because of the specialized training he had in metal casting, as I belong to the same profession when I joined this institute. I am indebted to him for his support as professor and HOD of the Department of Metallurgical Engineering and later as principal of KIUC. Even today, he is endearing to all of our family members. I take this opportunity to wish him and Mrs. Ramchandran sound health for many more years, and I hope the Department of Metallurgical Engineering, NITK, will continue to organize this series of lectures every year. Sir, Mr. Ramchandran, I'm not sure if I have met your initial expectations from me as I have drifted away from acquiring a theoretical understanding of certification science, which was your area, which is normally expected of a person in academics. Though I am in IIT Madras, my 10-year tenure in Tata Steel made me a different person. I have reasons to tell this. In the next 30 or 40 minutes of when I go through the slides, you will understand the world of difference between practicing engineering and teaching and doing research in engineering. I have personally gone through these two phases, and therefore I would like to put before you my experiences in both types of organizations, which I think is probably a unique opportunity I had. I have spent equal number of years in academics and in the industry, and there is reason to believe that, and I propose that the two approaches to metallurgical engineering, practice and theory should come together. There are opportunities for young engineers today to bridge this gap. I took upon my journey into the unsure area of process modeling for plant applications. There are process modeling. You have heard about, you are aware of the advances in computer applications or computer-aided engineering in other disciplines. Your sister disciplines like mechanical engineering, applied mechanics, civil engineering, where computer-aided engineering has made tremendous advancements ever since the advent of the digital computers. But as far as metallurgical process modeling is concerned, for computer-aided engineering, that is for process modeling applications, there is a fine difference, which I would like to elaborate on. I am a bit hesitant to present this lecture based mostly on my work in the last 30 years in close association with Tata Steel and others. Please accept this as a token of gratitude, sir, and I hope you will pardon me for a rather unconventional approach to mathematical modeling. I would therefore present to you a compilation of the work that is done. It is not a lecture which is truly of academic excellence. I must say this up front, and I apologize to you if there is any. If you are expecting a highly academic exposure to material science. It's not so. It is an engineering appreciation of metallurgical process. I would like to introduce the subject of process modeling in plant applications with an introduction to what is automation in metallurgical manufacturing processes. Automation is as its generic names tells. It is use of machines, use of digitizing information and then taking decisions, particularly using the computers today. It should not be confused to mechanization. Now, process models have a key role. First of all, I hope you appreciate what are process models. They are computer algorithms which capture the metallurgical theory behind processing, say, steel making or any other manufacturing process. You have basic and applied process models which can be distinguished. Academic institutions are very much advanced in the area of scientific process modeling. But by applied or engineering process models are slightly different, which are far more relevant to the industries. When academicians are interested in the analysis part, you take a process, you take a look at the physical principles deeply, and you go do analysis. There is need to synthesize various process models, and this results in a shift in the modeling approach. There is a paradigm shift in modeling approach, plant applications of concern. The approach to industrial process modeling can be regarded as sitting at level 2 process. They are intelligent applications. Then we will go to some of the key pointers in successful online process models. We will take examples where such integrated models have been successfully applied in the steel making industry, particularly in the blast furnace, continuous caster, plate mill, or strip mill, Banner table. These are all mega equipment where where a single process is not taking place, but multiple processes are taking place at the same time. Some examples I would like to take in the next few slides and bring out the difference between academic approach of process modeling, and the industrial applications of such models, where they fit in, what are their users, what is the real benefit for the industry from out of such models. Brief introduction to the multi-level automation system in steel industry. Now, the automation system is integrated into steel production process at various levels. Automation is only information handling. What is the information? It could be various parameters like temperatures, thickness of a strip, composition of steel, and how that information is processed throughout the processing, and then finally corporate decisions are taken. In other words, a particular steel grade, a certain tonnage is required by the marketing department on a certain date. How do you manufacture it? So even corporate decisions are taken together with the seamless integration through various models of automation. There can be distinct 4 levels and 3 levels of automation systems. At the bottommost in this pyramidal or hierarchical automation system, which uses computers, instruments extensively, at the basic level you have got basic instruments, sensors, temperature sensors, pressure sensors. From this, the information is handled and then finally you will know at the corporate level what type of steel is produced on a certain gauge, when can the delivery be expected of a certain grade, and such complex systems. Where do the process models sit in this? What are these process models are doing? These process models are to be developed by metallurgical engineers alone. Only metallurgists know about the processing. For example, hot strip mill, where the thickness of the slab is reduced in successive stages. Every metallurgical student knows about what happens when plastic deformation takes place, or when a strip is rolled between two rods and the thickness is reduced. What are the metallurgical phenomena? You have got recrystallization, then you have got various other aspects of the processes. All these metallurgical knowledge is to be captured in terms of mathematical models, and finally decisions are to be given to the equipment to manufacture goods or manufacture steel plates or liquid steel for a certain within a certain quality band or within a certain range of production ranges. Now, so the level 5 the level 0 comprises of all the digital times and other things. I'm now focusing on the level 2 process models. So process modeling can be differentiated in terms of what they explain. Basic scientific models capture the micro features of the individual process. When you look at, say, solidification. Now we all start with metallurgically we start with, say, a binary equilibrium diagram, an equidus and the solidus, and what happens to how the solidification takes place, nucleation, dynamics, kinetics, everything. But those equations that we come across there, which describes the solidification aspects, can be regarded as the scientific models. They are process models only. In fact, in metallurgical science, metallurgical engineering, there are many models which are not utilized by the industry. They all belong to the scientific point of view. But then when you look at industrial processes, they have to capture the macro features of the system. When the liquid metal is poured into a mold, what happens to the casting? You are not looking at the micro features of the solidification aspects. It has to be integrated with labeling processes. What do we mean by labeling processes? Simultaneously, things are changing. As the solidification changes, there are stresses changing. They are shrinkage taking place. So all these are the neighboring processes, and they are non-linear systems. They become equilibrium subsystems. Things are changing on a rapid scale. They are all unobservable processes. You cannot go and measure the temperature at every location. You cannot measure the stresses at every location. And similarly here, they are all interdependent processes. There is an intricate cause-effect relationship. These things can be explained with probably a diagram like this. If you look at the, say, continuous casting process, number of things are taking place. Strand solidification is at the heart of it. The solidification of liquid metal. But as it is happening, there is a great mixing taking place when the layers are changed, the steels are changed, the stresses develop in the strand, there is segregation, the heat transfer coefficient is changing, air gap is forming, So these individual islands can each become a research topic. When you go deeper and deeper into it, you will gain more and more explicit information about that singular process. Now that is where the academicians excel. If you look at just this basic transportation, it's a very major challenge to quantify how much is the heat transfer coefficient in the cooling zone. Similarly, stresses in the strand as the solidification is progressing, which will benefit the steel making chains and which will of course fetch them millions of rupees saved in rejection of the final steel, final layer steel. That is application which control the processes. They are very, very expensive. They are only practice this entire these models are available today in say in European and European countries, particularly Japan also, Japan, Korea and Europe have mastered these techniques and today it's valuable, and there is a major challenge and major opportunity for students to really go into these areas, which is a combination of many fields of interest. So here, the physical aspects of sub-processes, as I told you, many of the intricate processes you must understand, you must have a clear picture of the process. The tested models are all available, they have been used, improve upon the existing models, then identify key tuning parameters. It is not necessary to go to study the process by itself. The important thing is to see how the equipment behaves and fine-tune them with operating data. You have to have a close association with the industry for this. And you should use a lot of soft computing techniques like the artificial neural nets and theoretical algorithms, heuristics. Go to the experts, find out their the accumulated knowledge of the individuals, put them into a heuristic-based decision system, and then you develop the model for implementation in the practice. This has got challenges in software development, in soft computing, in understanding the metallurgy of the process, in being close to the process itself, to observe the process and develop these models. You will see that there is an iterative loop here. Tuning parameters are the ones which make these process models applicable to the specific equipment. Then the basic models are changed and you improve the algorithm, and finally the model for activity. Here, I would like to spend just a minute on this. The software engineering aspects. Now many of the experts are drawn towards the IT industry, but then let me tell you, there is a far greater challenge in core engineering applications today to develop the IT-based process models, and there is sufficient scope for computer science as well as software engineering skills to be developed for core engineering also. This is something which I think all the students have to bear in mind. So this I will skip. This is something which I thought can be a red flag to many of the people. What are the different skill sets that the students or the department or the industry should look in? I just made this list in order to bring out the place of the process cleaning, mathematical techniques, plant knowledge, field data. These are the key issues, and for engineering applications, mathematical techniques are important. Plant knowledge has to be extensive. We cannot develop these models inside from a laboratories. And interestingly, the field data they have to obtain, they have to get extensive access to field data. Field data is plant equipment data. The data that is collected from the sensors. And it all depends on software skills again. We have to have extensive software skills. And of course, today the graphical user interface has become a very important aspect, and therefore you must have an extensive computer language. And if you look at this, the process cleaning, which is important at the educational institutions, makes it an important part here. And I would say that process cleaning knowledge at the tech level at least is necessary to take up such tasks in the industry. So, first part I would say is metallurgical processes are extremely complex. Though the textbooks explain it in a very simple theoretical approach, the processes are very complex. Heat transfer, fluid flow, high temperatures, non-linearities, thermochemical metallurgical reactions, for example, transformation, scans data. You don't have good information coming to you as to know what is happening in the process. Unobservable processes. If you look at steel making vessels, it's unobservable processes. Mathematical modeling is very, very involved. And simple models needed for nano operating, which is another important thing. Any equipment in steel making or any other, say, including, say, presses, forgings, whatever, these equipments are built only to produce certain varieties of goods, certain varieties of components, a very specific range of operating conditions. That is why it is possible to develop simple models which operate only in a certain narrow range. It cannot be extended to any other system. It is specific to the equipment. So mathematical must combine with heuristics, plant tuning, and software engineering. Tested models are highly valuable. Now, there is now a lot of appreciation that our country has to develop our own models, because in practice, at least it has been my experience in dealing with major steel plants, that when they go with a shopping bag to get these models from the advanced countries, they get only outdated models. So that means the models which have run out of their expertise or have lagged behind at least dozen years is only available in the market. So we have to develop our own models, and this is where again a lot of opportunities exist. So they are highly valued in process design, new materials, new grades of steel are being required, how to make thermomechanical processing possible, how to narrow down the chemistry of steel. These are all challenges today in these types of industries. Cost effectiveness, consistent quality, and other issues. I will now come to briefly, I've got a few slides with me to tell you about some of the initiatives which our steel plants have done in the past 15 to 20 years. These are all long processes involving many big organizations. You all, I'm particularly the students of the blast furnace, you know the construction of this. Here, two important factors are there. One is how the material is distributed at the top is of key importance to the continued working of a blast furnace. You will be amazed to know that blast furnaces, once commissioned, have to be producing consistently tons of liquid iron for years together. The demand on work is extremely high, and the consistent operation is very important. And one of the key factors is how the sinter and the coke is distributed at the top. Now the top of the blast furnace is inaccessible. You do not know where the material is falling. And to assist that, we have what are known as the burden distribution models. These burden distribution models, I will give you some photographs which we took from the Bocaro blast furnace. These are chutes, which are semicircular chutes, which rotate about a vertical axis. This is the top of the blast furnace. The material is continuously being discharged from the top, and as it rotates, it distributes. Its angular position also changes. These are called forward distribution systems. Now, you will get a stream of this material. See, if you look at the fundamental aspects of how the granular material flows under the effect of gravity, this problem can be made any complicated. It can be made as complicated as we wish. Why? Because granular materials are subjected to flow of gravity. Due to gravity, they flow, they bombard with each other, there is collision, there is loss of kinetic energy. Where they fall, you do not know. But very simple models can be developed by considering a single particle. This is pure dynamics. This is only maybe at the high school level you have learned about the flow of a material or there is a centrifugal force acting on a particle which is subjected to rotation and things like that. Fourier component you all know. So the simplification is done by these are the factors that are affecting burden distribution, friction characteristics of different charge materials, size segregation. When material comprising of different granular materials, granular sizes, there is a size segregation, velocity spectrum, widening of stream, percolation of final material, layer compaction, effect of gas velocity. All these things are quite complex to model fully. On the other hand, even very simple models which look only at the dynamics of simple particle that is called a single particle. You don't have to look at the entire spectrum of the particle size. Will give you sufficiently good models for explaining the trajectory of the material. So there are the many forces that are acting on a single particle in a semicircular chute. If you analyze this velocity spectrum and look at where the material is falling, look at how the material falls over, you can find out the peak shape. Now this is something similar to what you see in many of the roadsides when you see the burden layer. That is, when the material falls, the larger particles roll over, and as you move away from the point of impact, there will be a lot of, the porosity distribution will change, and there will be gas flow changes and so on accordingly. The particle size distribution at different locations will have to be modeled. Out of this, you will get, even by simplifying all the process, you will get to know how the material builds up at the top of the blast furnace. Once you know this, you know how the gas flows in the interstitial area, and you will see, and we can find out the effect of distribution on the porosity or on the pore output ratios and other aspects. Now, such models will help the steel industry, essentially the upper plants, to control the processes. And these are some of the simplified models that have been developed today in the steel industry. And experiments are difficult. These are some of the photographs that are taken from the top of the blast furnace. You will see how the particles are falling. These are coke particles. This is iron ore particles, sinter particles. There is already, you will see a distribution here. The finer particles are here and the large particles are pushed on the other side. And to validate, some of the very simple techniques are used. Now, this is the top of the blast furnace, where a rod is not coated with just chalk, just a white paint is introduced, and by looking at the area that are marked by the falling particles like this, the spread of the stream. Quite far, the experimental techniques in industries are very, very simplified. So you must have a very, these experiments cannot be extended to the laboratory type of experiments in the plant. So this is a different kind of modeling, it's a different kind of acquiring data and using the mathematical, using the models. Now, another important aspect of blast furnace operation is how the wear takes place in the blast furnace. As I said, for years together, the iron will have to be evacuated, or rather taken out. Now, the bottom construction, the construction of the bottom of the blast furnace is made with refractory, sometimes even carbon bricks. They have to withstand the stresses that are developed through the flow of iron. Now, we do not know how much wear takes place. It's very difficult to measure how much of wear has taken place. If the wear is too much, then there may be major catastrophic accidents with what is known as blowouts. So the liquid metal will come out of the lower part of the earth, and there will be major damages. So in order to predict this, one approach would be the CFD approach, which involves major mathematical equations, unsolvable in many cases. But we have to simplify this, and simplified models have been developed using embedding thermocouples along the wall and the earth of the blast furnace, looking at the temperatures and solving for the front inversely. Looking at the temperature, you can say how much is the temperature, or where is the wear taking, where to what extent the wear has taken place. These Hart model wares, the Hart wear models have also been developed with much simplified approach using inverse models. Of course, the equations are there which describe the heat conduction equation, and then it's all inverse. The computerized terms you will get, and you will see how day to day the wear can change. The shape of the wear in the furnace heart can be extremely complex and can be quite complicated. This is another example of an application where you have to interact with the client and get data from the field and use models which are quite simplified. This is another area, this is another model which will tell you how the wear is going. Now another application is the continuous casting mount. People who are introduced to the subject know that the heat transfer in the open mold of a continuous casting machine can be extremely complex. This is the copper mold which is in touch. The steam is continuously being fed from the top and the flowing downwards. Then it is the submerged entry nozzle which creates a voltage-free pool of the circulation, and there will be the flux powder which is drawn into the interstices and creates a thermal barrier here. Now, heat transfer from the liquid steam to the copper and from the copper to the water here can be very complex, because it has to go through a solidified shell, it has to go through a pre-solidified flux layer, and then to the copper, and then. So if you look at the physical aspects of this, the mathematical models can be very complex. Look at this. You have got, if you look at the flow set up by the submerged nozzle into the liquid pool, and then how the viscosity affects the flow of the solidified flux material. We have got both liquid flux and the solid flux. How the heat transfer goes through, how the heat transfer takes place, very complex. Look at another type of model, which is known as the inverse model. You just put some thermocouples in the bowl, look at the temperatures, and using the same conduction, simple conduction equations, you can find out how much to take in flux. The heat flux distribution in the copper model can be easily obtained by the inverse modeling techniques. So, the hot strip mill is another major equipment in steel plants. Generally, the slabs are heated in furnaces, slab reheating furnaces, and goes through a series of roughing mills. Either it could be a single stand roughing mill or a continuous roughing mill, where the thickness of the slab is reduced to 50 to 20 millimeters, and then goes through a series of finishing mills to produce steel strips, which can be several a kilometer long, and then finally rolled here. And you have got another tandem equipment, the runout table, where the strips are cooled, which is essentially a thermomechanical processing. All these again involve all your theoretical models, the theoretical processes that are involved in loading. For example, the loading loads are changing, re-stabilization dynamics, rolling gap, roll gap, heat transfer is changing, and you have to quantify all these things using various types of models. The flow stress models can be estimated through various alternative rules. Each one has certain features like hyperbolic function having parameter estimation, troubleshooting aspects built into them or embedded in them. Rolling load calculations can be done in different ways. Strip pooling modeling also can be done. These models have already been already available in the literature. You use these models available in the literature and put them together and use models that use plant data to tune the parameters, and then finally the constructive models can be usefully employed in the plant. Some of the data that has been validated are shown here. Including the strength and other properties of the steel can be modeled using such models. And I come to the last one, the adaptive mathematical model, thickness control in the plate mill. Now the plate mill is one where the rolling process actually is the main process. The roll pass design is a key issue because the temperatures are changing with each pass, and as the temperature comes down, the force stress increases, the rolling load increases, and the roll strength is smacked like fish in actual plant practice, in plant operations. To control these things, we should have a clear idea of the various conditions under which the slab is being processed. So the strain rate, the rolling loads in each pass, the roll torque, the motor power, plate temperatures, plate length at the end of each pass must be calculated. And in each bite, that is, when bite is actually when the plate is being rolled within the bite, from the entry to the exit, the strains will change, the strain rate, the plate temperatures will change, rolling load. Of course, this is not the curve is not seen here, but it has to be estimated. For this, you have developed a moving coordinate system which will track all these parameters from the front end to the end, the front and the end of the slab, the final plate. You will see that the process, each place, the position of the slab at the end, at the beginning and the end are different, and you will see the processes the parameters are all changing. And you should develop a moving coordinate system to quantify these aspects. Now, the important thing in this is taking decisions and changing the set points in for the equipment, for the subsequent rows. If the conditions have changed, then the models must adapt themselves and change the operating conditions suitably so that the quality and fitness control is maintained. And finished mill entry also, the rolling mill and the roughing mill and the finished mill at the entry and the exit, they have to be properly controlled. So class parameters have to be controlled. Slab to slab adaptation, that is, each slab becomes different in its characteristics, the temperatures and everything. Class to class adaptation has to be done. And finally, you have to set the roll gap. The roll gap set, rather the automation actually controls the entire equipment is controlled by signals from the computer. The computer, the automation says, okay, change the set point. The set point is one which controls, it downloads the information to the process, to the equipment. So here you will see how the simulator will operate. This is the furnace, it mimics the furnace, and as the furnace, as the slab drops out from the furnace, immediately the sensors will sense that the slab has come, and it will compute what will be the expected process conditions after each row. Each one of these boxes represent in the computer, which is available in the automation space, an equipment. This is the edger, this is the T-scaler, this is the roughing mill stand, this is the temperature sensors, and this is the finishing mill, and things like that. So, as steel travels through each one of these processes, for example here, you will see that the conditions are changing. So this is an indication to the operator as to what might happen, and behind all these things we have got these process models working online. So the process adapt to from 11 to online simulator. Then we have have got the model validation. Summary is this: mathematical models for applied calculations have been developed, and in spite of the roll forces have been measured, utilized in all utilized roll forces. Thickness between the corners will be achieved in 81% of the cases in this case. I was a little not sure after that, and I'm sure there will be a lot of questions from my young friends, particularly. Please ask, and they are able to. I'll be glad to clarify whatever questions you have, and this very important, applications of your knowledge for the industry. Please, with this I stop. I'm also not. I'd like to stop here and ask for any clarification.
If you have any questions, any clarification, you can ask.
Any clarifications, Shika? I chose this subject. I must say here that I've chosen this subject only to indicate my young friends, particularly from the students. There is a lot of opportunity in the industries today, in the core industry, particularly in the applications which are very challenging. It doesn't mean, the core industry doesn't mean that you have to soil your hands all the time. This is what I wanted to tell you. These are some things which will give you a lot of satisfaction for applying your knowledge and also pursuing very greatly intellectually satisfying activity.
Interdependent process, right, on the other process. It's just heat transfer or phase transformation.
Yeah, it is still okay.
Now, you said you classified field data and lab. You told field data and lab data are not so valid in scientific and engineering field. So when you can scale down them to bring it, like you can do it in a lab also, right? When you can scale down that process, they are not interdependent.
No, I'm okay. Okay, what's your question?
So why do you say that? Like, why did you say that you need extensive information here?
Now you are looking heat treatment from the lab angle. Now think of a forging industry or a steel casting. That's where I'm telling you to visit. Let me tell you one thing. There are heat treatment you are looking at only when you are learning as a student. When you go to plant, things are totally different. Let me tell you how you go to a forging industry or a steel casting industry. The casting weighs tons. It is an extremely complicated shape. What do? They don't have control over the quenchant, in fact. The quenchants, actually, some of the quenchant tanks are about, the tank itself is this big. It has about 20 feet wide by maybe 40 feet. It takes a finite time for the casting to get immersed. Temperature is continuously changing. That is what plant application is all about. And when you look at that process in the plant, and when you look at what you have learned at the heat treatment through that chapter, there will be a wide gap of application, You have to bring that knowledge, what you learn in the classrooms, when you apply it to that fuzzy area. You cannot define many things in the plant. That is where the difference, even in heat treatment areas, today in forging industry also, there is marking. People would not know. In fact, let me tell you, many of the industries, many of the people do not know why certain things are not happening as they expect. There the modeling will set up it.
These are the students. From the fourth year, the topper is Mr. Vinay Kumar Thakur. Since he is not present here today, I request the class representative of the fourth year. From the second year, we have, from third year, we have Mr. Pranav Nayak. And from the second year, we have Mr. Jubin Surana.
No one likes that.
Thank you, sir. We are now coming to the end of this program. I request Akashvi Nair to please come up on stage and give a vote of thanks.
At the outset, on behalf of the MA, Department of Metallurgical and Materials Engineering Department, NITK, faculty and students, I would like to thank all the respected dignitaries present here today. I thank Professor T.R. Prasanna Kumar, who gave us this wonderful talk. Thank you, sir. I thank Professor T. Ramchandran, in whose honor we hold the talk every year, for being a guiding light for our department and for his constant presence throughout the years and today. Thank you, sir. I'd also like to thank Professor G. Umesh, sir, for presiding over the function. I also thank all the ex-faculty members of our department who have come here, taken the pain to come here, and also present faculty members whose presence here has made this function a success. I also thank all the students, the research scholars, and any guests who is present here, without whom this function would again not have been a great success. Thank you. I also thank Watch and Ward for providing us the facilities for conducting this event. Thank you.